All right, get this. What if our data centers, the engines powering AI, could do way more than just compute? What if they could also clean our atmosphere and build the materials of the future all at the same time? Well, today, we're diving into a design that does exactly that.
Yeah, I know. It sounds a little bit like science fiction, right? But the core idea is actually pretty simple when you boil it down. What if we could literally build the infrastructure of our future from thin air? That's the huge, audacious concept we're digging into.
So, we're talking about a single integrated facility that powers AI, cleans the air, makes fuel, and builds advanced materials. It's the whole shebang. And here's the kicker. This isn't some far-off dream. The technologies to make this happen aren't decades away. They're either ready to go right now or in the very final stages of development.
Okay, so how on earth does this all fit together? Here's the plan. We'll start with the big picture, the all-in-one hub. Then we'll look at the synergy between sun and silicon, see how it generates power 24/7, turns carbon into valuable stuff, and finally, how it creates this incredible self-reinforcing flywheel. Let's get into it.
All right, first up, the all-in-one industrial hub. So, what exactly is this thing? Well, it's not one single magic invention. It's actually a super clever integration of technologies that already exist. By putting them all together in the right way, you create a system that is way, way more powerful than the sum of its parts.
The secret sauce really is what's called colocation, which is just a fancy way of saying you put everything in one place. I want you to picture a giant solar farm right next to a data center, right next to a chemical plant. They're all physically connected, sharing energy and resources like a single organism. This creates this beautiful closed-loop system where the waste from one part becomes the fuel for the next.
Okay, let's dive into the first piece of the puzzle: sun, silicon, and synergy. We'll start with two things we're all pretty familiar with: a massive solar farm out in the desert and a super power-hungry AI data center. Now, on their own, they each have their own set of problems, but when you put them together, that's when something really elegant happens. So here's the problem. Modern AI data centers are absolute powerhouses, right? But they're also basically giant furnaces. They suck down insane amounts of electricity to run, and then they have to use even more electricity just to cool themselves down. And what happens to all that heat? It just gets dumped into the atmosphere as waste. It's incredibly inefficient. But this is where the whole paradigm shifts. Instead of just throwing that heat away, the hub uses a really advanced cooling system. It's called supercritical CO₂ cooling. Basically, it uses carbon dioxide under intense pressure. And the cool thing is, it captures that waste heat at a really high, really useful temperature. Suddenly, that heat isn't a problem to be gotten rid of. It's a valuable resource that can power the rest of the facility.
Okay, so we've got the data center's waste heat handled. But what about the rest of the system? We still need a ton of reliable energy. And that brings us to solar power's biggest, oldest weakness. What happens at night? See, at the very heart of this hub, there's a carbon capture process. And there's a key piece of equipment in there. It's called a calciner. And to do its job of pulling CO₂ out of the air, it needs a steady, constant stream of super high temperature heat. We're talking around 900 degrees Celsius. That's a huge problem if you're relying on solar power, which, turns off every evening. And you can see the effect right here. If you tried to run one of these carbon capture facilities on solar power alone, you'd only be up and running maybe 30% of the time. That's just not going to cut it. But with one key addition, that uptime skyrockets to over 90%. So what's the secret? The solution is something called high-temperature thermal energy storage, or TES for short. The best way to think about it is like a giant rechargeable thermal battery. During the day, when solar power is cheap and abundant, it soaks up all that extra electricity and uses it to heat up simple things like insulated bricks or carbon blocks to insanely high temperatures, over 1800 degrees Celsius. Then it just steadily releases that intense heat 24/7, giving the carbon capture system the constant energy it needs to run around the clock. Problem solved. All right, so now we have a steady 24/7 source of intense heat. This is where we get to unlock the real chemical magic at the heart of this hub, actually turning the CO₂ from the air into valuable, useful stuff. So here's how the process works, step by step. First, these special units use that heat from the thermal battery to capture CO₂ directly from the atmosphere. Then, they take that CO₂ and combine it with green hydrogen, which is also made right there on site, to create synthetic methane. But, and this is a really cool part, Instead of burning that methane for energy, they use a process called pyrolysis. They basically crack it with heat, splitting it into two super valuable products: clean hydrogen, which gets recycled right back into the process, and pure solid carbon. Okay, and this is where the whole system goes from just being smart to being truly visionary. It's not just about making valuable materials, it's about creating a feedback loop that makes the entire system better and more efficient over time. It's a self-reinforcing flywheel. Remember that solid carbon we just talked about? Well, it isn't just some waste byproduct. It's actually a super valuable feedstock. It comes out in the form of carbon nanotubes, or CNTs, which are then spun into this revolutionary supermaterial called galvorn. And this stuff, it has some truly remarkable properties.
Just how advanced are we talking? Well, for starters, it's 80% lighter than copper, but it's just as good at conducting electricity. That is a total game changer, especially for things like wiring. The hub can literally use the material it makes to replace the heavy copper wiring in its own solar farm and data center. And that leads to this perfect feedback loop. The source document puts it beautifully. It says, more CNTs enable better MOF sorbents, which capture more CO₂, which yields more CNTs. In other words, the carbon nanotubes the hub makes can be used to improve the very materials, the sorbents, that capture CO₂. It's just perfect. Yeah, just let that sink in for a second. The hub's output literally becomes the input for its own improvement. The more of this advanced material it makes, the better it gets at capturing carbon. And the more carbon it captures, the more material it can make. It's this perfect self-reinforcing flywheel that gets cleaner and more efficient with every single cycle. So what does this all add up to in the real world? What's the economic and climate impact? Well, this isn't just some elegant engineering project. It is a powerful and really resilient business model for a completely new kind of industry. The financial brilliance here really comes from having multiple stacked revenue streams. Think about it. It makes money from data center fees from AI clients. It can sell synthetic methane. It gets tax credits for capturing carbon and making hydrogen. It sells the high-margin galvorn material. And it can even make money by helping to balance the electrical grid. Having all these different income sources makes it so much more financially resilient than a facility that just does one thing. So what's the bottom line here? What's the real impact? Well, first, carbon gets permanently locked away, sequestered, in high-value products like wiring, not just buried underground. This also means you're displacing carbon-intensive industries like copper mining. The whole campus achieves over 80% energy utilization, which is just incredible. And ultimately, it creates a real, tangible blueprint for how heavy industry can become carbon negative. And I just want to be crystal clear about this. This is not science fiction. This isn't some pie-in-the-sky idea for 2050. Every single component we've talked about is either commercially available right now or is in the late pilot stage as of early 2026. This is ready. The first hub could start construction today. You know, what a system like this really shows is that maybe our biggest industrial challenges, data, energy, and materials, aren't actually separate problems we need to solve. Maybe they're just interconnected parts of a single, elegant solution. And that really leaves you wondering, doesn't it? What other amazing synergies like this are just sitting there, waiting to be discovered?